off, I'd like to apologize for bringing the snow with me from Colorado. So, yeah, as pointed out, spent 12 years working on the Spirit and Opportunity rovers at JPL and a brief 6-month stint on the Curiosity rover, which, for context, the only rover that's on Mars right now that I have ever seen was the Curiosity rover. The Spirit and Opportunity rovers were built when I was in college. They launched before I graduated, so I had never actually seen the rovers I drove with my own eyes, which is an interesting thing when you become that attached to those vehicles. So, as Don told me, kind of got this presentation in 2 parts. The first part is going to be a lot more about the experiences at JPL using the book and movie The Martian as kind of a pop culture reference because the science in it was really accurate, and a bunch of us started having discussions of if this was real, how would we handle it at JPL? If we found out there was an astronaut stranded on Mars and needed to drive a long distance across the planet, what would we be doing to help that astronaut out? And the second half is going to kind of dive into space resources, which is a fairly new field. And I'll cover how we've actually been using space resources since the 1950s, even though we didn't call them space resources at the time. So starting off, this image is a promo shot from The Martian. So 20th Century Fox did a really nice version of the book in movie form. And I think the big spoiler of all of these ventures is if you take Matt Damon with you, you'll get rescued. If you don't have Matt Damon with you, you won't be rescued. So the book starts off a little bit farther in. The book actually starts off with a expletive, but at this point, Mark Watney's stuck on Mars and starting to realize the problem and talking about how it's a barren wasteland and he's the only person there. Nothing but dust, rocks, and endless empty desert in all directions, which is a pretty good description of all of the planet right now. And this image is from the Pathfinder lander from 1997. So in the book, Mark Watney has the main concerns of how much food and water and power he needs to, not die on Mars, how to build an RV to drive across Mars, how to pack things into that RV, and also being fairly eloquent about all of those mundane tasks and when they go wrong. So he's pretty much turning this rover into a Volkswagen camper. So down at JPL, this is the group of the 3 of us that had lunch and started thinking about how we'd actually do this. So Fred Califf is the keeper of the maps. That is his official, kind of unofficial job title with all the Mars missions. He doesn't make all the maps, but he is the one that coordinates all the maps. Serena is a planetary geomorphologist. That means she looks at the shapes of features on Mars. So sand dunes, craters, hillsides, all of the things that we either need to drive over or drive around. So she's a very handy person to have on your team when you're planning out routes on Mars. And of course, I'm the rover driver, so I'm the person that has to try and drive around those or gets in trouble if I accidentally drive into a sand trap. So the things we really care about are that we have this nice smooth flat terrain. It's a lot easier to drive down a highway than it is to drive off-road. Good visibility, that's important both on Mars and on Earth, even though we're going slower. And clear skies, that helps us generate power. Spirit and Opportunity rovers and the tiny little microwave-sized Sojourner rover before it were solar-powered. The Curiosity rover has a big plutonium battery, so it doesn't care as much about sunshine. But if it's a cloudy day, you don't get as many shadows, and that actually makes it harder to look at the terrain in front of you and see if there's anything you may run into or need to drive around. So even if you're nuclear powered, you do need to have those clear skies to help drive. So those are the things the 3 of us really care about. So for context, we have 2 very standard metric unit engineers standing in this photo. That's Wes. I worked with him actually on the urban search and rescue team at JPL. So Wes comes up to about my ear height for context. And there's 3 generations of rovers. The small one is the Sojourner rover size. The medium size is Spirit and Opportunity. This is the test bed stunt double for Spirit and Opportunity. So it doesn't have the solar panels because normally it's inside and plugged into the wall. And then you've got the ground test unit for the Curiosity rover, which is also normally plugged into the wall, except for they have a big extension cord so they can drive it outside. In this photo, one of these is actually a real spacecraft. That's not the Sojourner rover. That's a rover that's named the Marie Curie. Had they dropped Sojourner when they were building it and broke it on the floor, the Marie Curie would have gone to Mars instead. They almost sent it in 2001, but we had a couple big failures in 1999, which caused JPL to rethink the entire Mars program. So that one is now no longer sitting at JPL in the dirt. It is in the National Air and Space Museum in Washington, D.C. So the story of the Martian kind of takes place in this rectangle on Mars. Sedalia Planitia is where the movie and the book start. That's where Ares 3, the fictional crew mission, goes. And then down here is in the Schiaparelli crater is where the Ares 4 mission that would have followed is. So that's kind of our setting for this whole adventure across the surface of Mars. The big black dots, that's where the Pathfinder rover landed. Lander and Sojourner rover were up in the top left, and down in the bottom center is where the Opportunity rover was. And my former colleague Fred likes to point out that those two dots are located down to about a 1 meter accuracy, despite the fact they are several hundred kilometers in diameter as shown on this map. And the part that kind of Fred has some qualms with is talking about the maps. Talking about how he only has satellite images that can show things about 50 kilometers across, which means that's about the only map of Mars that the movie and the book have to navigate by. And finding landmarks. It's hard if you don't know where the landmarks are on the map, but it's easier if you can actually see things. So if you land on a big flat plain, it's harder to see craters that are holes in the ground as opposed to hills that poke up above. So Fred, being the keeper of the maps, made all of these very nice maps you're going to see. So every map you see from now on is going to be the same exact area, just with either different color scales or trying to show different information. So again, we've got Ares 3 way up at the top, and the Ares 4 MAV is the Mars Ascent Vehicle, way down here at the bottom. So that's a pretty long distance to drive across. Since that map with just the color as you would see it taken from old Viking images is not as useful, we have a topographic map of Mars now. In 1997, when the Mars Global Surveyor arrived, we ended up with a laser altimeter on board the satellite. So shoot the laser beam down at the surface, measure how long it takes for it to reflect back up, and it would do that millions of times throughout its mission, and it built this high-resolution map of the surface of Mars and the altitude. So to code that map, blue is low altitude, red is high altitude. It's several kilometers difference. And with this, you can really start to see the depth of craters. And you can see river formations, Ares Vallis, where Pathfinder landed at the end of, you can see is a deeper canyon that cuts across. You can see the bigger hills in red down by the Ares 4 site by Schiaparelli crater. And you can see the depth of the craters in what the book called as the Watney Triangle. Unfortunately, the movie skipped that whole part of the drive across Mars. So taking pictures of Mars from Mars orbit, that's what we use to plan out the drives. That's what Fred makes the maps off of. And our resolution has improved. When Viking first got there, we kind of had 200 meter to 12 meters per each pixel. So you can lose a lot of detail. You can hide rovers in that. You can hide craters in that. It's a bad day if you are trying to pick landing sites on that, which they actually did for Mars Pathfinder. They just bombed into their location. They didn't know that all of those big rocks were going to be there that could rip open the airbags used for landing, because that's the best information we had at the time. Then in the 1990s, we got the modern Mars program going again with Pathfinder after a false start in the early 90s with a failed mission called Mars Observer, and we started getting better resolution. But this table, while it gives some information about all the different cameras we used to have and all the different science instruments we still do on various orbiters, and it's categorized by which lander era you're in, doesn't really tell you much. I mean, there's a lot of information here, but it's not really intuitive. So let's divert into a little bit of what the resolution would look like if you were taking pictures of Mars. So we'll just pretend that Mars is a nice big white plane where you've got these two astronauts standing on it. So if you're Viking and two astronauts are standing in the middle of your one giant 12-meter pixel, that's what it would look like. You can't really see anything, and believe it or not, that rectangle, that square is slightly orange, very slightly, because you wouldn't be able to see them. All right, Mars Global Surveyor, we're getting a little bit better. Slightly more orange, but not much. So you still can't see that these are astronauts. The better camera on Mars Global Surveyor, which gets down to about 2 meters per pixel, you have a slightly more orange square. Mars Reconnaissance Orbiter is the best camera we have around Mars. It's a 1-meter telescope looking down. And let's just zoom in on the astronaut in the orange because the one in the white doesn't make for a good demonstration. That's about what that astronaut would look like. So you can still tell there's something there that's got different colors and everything, but you still can't tell it's an astronaut. But that's looking down from 200 kilometers up in space. So the fact you can even see the astronauts 4 pixels across is a little bit better. Nice part is if an astronaut was standing up, you would be able to see the shadow on the ground. And if you know what you're looking at and expecting to be looking at, you could say, hey, there's an astronaut walking around down there. Maybe we forgot somebody. This is an actual picture from Mars Reconnaissance Orbiter taken in 2006 with the Opportunity rover. I was actually on vacation from JPL. I was in Boulder, Colorado with some friends when this image came down to Earth. I logged in remotely and took a look at the image, and the fact that even if you know what you're looking for, you can see the rover. Zooming in, there's the solar panels and the camera mast shadow. So when I said you could tell, because we know the sun's over here, so the shadow's over here, and we know that there's this nice big T-shaped camera mast that sticks up above the rover. So we could squint at it and figure out what we were looking at. There's a selfie of the rover taken looking down from its camera mast as a comparison. So you can see that, yep, there's a Mars rover. If you look really closely in this image, it's still kind of hard to see. You can see the tracks of the rover coming out and around. This was incredible because for the first couple years of the mission, we had never seen the rover's tracks on the surface from orbit. Now we could track them and see how they fade over time and also make sure we know where we were at. And Mars Reconnaissance Orbiter is still there, still taking images, and there's a few more in this presentation. So with all those cameras we have on Mars, we haven't mapped the whole planet in that nice high-resolution detail. So while this plot map looks like that it's got a case of the measles, the cream color is coverage from a camera, which is the context imager on Mars Reconnaissance Orbiter. So it can't see those details. It can see things about 6 meters across. So to give you an idea, this auditorium would be about 6 total pixels as seen from that camera. And all the red dots are areas that have been looked at in detail with the high-rise camera, the one that can see the rover and see rover tracks. And just because it's got such a narrow field of view, you can only see a little bit of the planet at a time. Thankfully, after 14 years at Mars, you're starting to build up more and more of these. The areas that have clusters are landing sites that were considered for future rovers. So when scientists really want to take a look at something, it tends to cluster around wherever you want to send the next rover. And it's nice because we even look at old rovers, like Opportunity got a good amount of coverage, Pathfinder they looked at, Marth Vallis was where they were thinking about sending the Curiosity rover. So those got a bunch. Same with Aram Chaos. Those are all areas that got extra coverage. But that takes time and effort to make sure it's the right season and everything. So that's gives you an idea. We can see most of Mars at 6 meters per pixel. And some people that are planning missions in the future to send, hundreds of humans there start looking at that lower resolution imagery and go, we found a great place to land. And then they get the high resolution imagery and go, it's full of boulders. We can't land there. So knowing which images are taken by which camera is very important in our world when it comes to looking down at the surface of Mars to plan a drive across the planet. So when The Martian came out, of course, NASA was excited because it's a movie that shows the agency in an incredibly good light. So they helped out quite a bit, including taking pictures of the landing site for the fictitious Ares 3 mission. So there's some references. The left side of this is one of those lower resolution 6 meter per pixel images with the footprint of the high resolution image on top of it. and the high resolution's off to the right. So we'll zoom in into part of that where those two craters were. I'll back up just a second so you can see the two craters that we're zooming in at. And decided on this knowing the scale of the image. In the book, the habitat has a good description of its size. In the movie, it's about the same. It's a circular thing. So that's about the size the habitat would be on the surface. And if you zoom in to the image even more, you can start to see these rocks on the edge of the crater rim on the inside. You can see ripples in the sand in the bottom of the crater. So we can see a lot from Mars. And this camera can take color pictures, but it can take more pictures with black and white. So a lot of the images we do get are black and white initially. So one of the things that plays into the book, not so much in the movie, is the concept of tracks disappearing. So Watney's hoping that when he drives down to Pathfinder, he'd be able to follow his tracks back and not get lost because, the terrain's smooth. If you already know the path you went and the route you drove there, it's easy to backtrack and find your way out. But he found that his tracks had disappeared, which somewhat happens on Mars and sometimes doesn't. Oh, there's the Curiosity rover down at the bottom. That's another one of those high-resolution images. It looks this color is more blue because it's taken out with a little bit more of the infrared and the ultraviolet light and combined into an image that we can see. So the infrared becomes red in this image, the ultraviolet becomes blue, green stays green. There's not much green on Mars. So we can still see the rovers. So they sometimes show up more blue than they are. So tracks sometimes disappear and sometimes don't. When Opportunity was exploring Victoria Crater, that one that I showed you the picture of it parked on the rim of, there was a big global dust storm. This was in 2007. It was, although now not a terrible global dust storm, it was perfectly survivable, and Opportunity and Spirit did survive. But it kicks a lot of dust up into the atmosphere of the planet. In fact, from about 60 degrees north to 60 degrees south, the atmosphere is completely full of dust. The sun is almost impossible to see. And we had left some tracks. The nice part is we were able to look at those old tracks because the atmospheric scientists wanted to understand how much dust was deposited. And the tracks from 2 years earlier in this image were pre-dust storm, and you can still see them. I mean, they're not as fresh as the brand new tracks, but you can still find your way home. So depending on where you are, you may be able to just follow your tracks back, even if it's a couple years later, not just 3 weeks. Or if you're on the other side of the planet like Spirit, this is during its dust storm experience. In 11 sols, the tracks were gone. So depending on the weather that was happening during the drive down to Pathfinder in the book, those tracks from the rover could have completely disappeared. Another big problem is craters. This is for rovers of all size, and Mark Watney talks about all of this, needing to drive around and up and down and through craters. So driving down into a crater will say you don't use quite as much energy, but just like a car going uphill, you have to give it a little bit more gas to get up the hill, which is a problem when you have an electric-powered rover that has to recharge after every drive. We tend to try not to drive the actual Mars rovers through craters for the same reason. So that was one of the concerns. And driving on the slope is dangerous. I am currently one of 2 rover drivers to hold the record for driving a rover on a slope. We reached a 32-degree slope unsuccessfully. We were trying to drive straight up it. It was a bunch of gravel, and gravity won that battle with us. So we ended up having to abandon a science campaign because we just couldn't drive the rover up that hill. And you don't want to risk rolling the rover. Most of them are fairly stable, but since the ones in the movie looked a lot more like a top-heavy SUV, that is a concern that would be real for him. So, back to how are we getting Mark Watney from Ares 3 to Ares 4 so we can have him picked up by the crew in the Hermes? Well, the shortest route across the surface is this Great Circle route, which goes right through that Watney triangle that keeps getting mentioned. And as you can see, it goes right through some craters. Many craters. Lots of craters. Right down the steep edge of Schiaparelli crater. That's not going to work because for any of you hikers out there, you've probably looked at elevation profiles, and this one goes down and back up and down and back up and down and back up, and I don't think anybody really wants to take this route. It would be a little bit more painful to go through, and those are pretty big elevation drops. This one drops down to, from Martian sea level, it's 3.5 kilometers below Martian sea level. And to get back out, that's climbing a full 1,000 meters out of that crater. These are deep holes in the ground. So that was part of what caused this map to be made at lunch one day. So Fred, Serena, and I started looking at it going, all right, you can't take the direct route. So how would you go? And this is what we came up with for a route that avoids a lot of craters. Also shown is the drive down to the Pathfinder rover, because without that, Mark Watney's not able to phone home, and we can't help him if we can't talk to him. So Fred, being the keeper of the maps and having all of the elevation data at his fingertips, immediately puts together a new elevation profile for what we've started calling the Watney Traverse. And it smooths out a lot of those couple kilometer drops into craters and then climbing back out. It's still not easy. You're gaining about 4 kilometers of altitude all the way across the drive, but it's more manageable. And the reason you want to avoid craters, so this is the approach to Victoria crater in 2006. So I joined the mission in August 2005. Opportunity had not yet reached Victoria Crater. It was out on the plains of Meridiani. And this is one of the first pictures we had where you could really tell there was a crater there. And it's a very old crater, so it doesn't have a rim sticking up. It's just a hole in the ground compared to the flat terrain around it. So this is from 50 meters away using our cameras. And the top image is made up of 6 frames of our 45-degree field of view camera. So we're getting a nice wide context idea. But zooming in one of those frames, you can see that, okay, there's something on the horizon. So from 50 meters away, there's something there. You may start to worry about it. From 200 meters away, okay, it's a crater. I don't know how deep it is. It's just I'm coming up on it in a hurry. And of course, when you're parked on the rim, you look and see there's these nice big cliffs that I really do not want to drive my Rover off of. For context, if you're going 60 miles an hour, you cover that 50 meters in 2 seconds. So rovers on Mars go only about a meter a minute. They're very slow because we want safety to be involved. But with a human driving, they may go faster. I'm not sure you'd see them going 60 miles an hour, but you want to make sure that you don't have the cruise control on and aren't paying attention to the road in front of you, because it could be a very bad day if you drive off one of those cliff faces. Sand is another problem that we encountered. This is from when Opportunity, right before I started at JPL in 2005, got stuck in a sand ripple. I believe the way it was described that the drives they were doing, that it was commanding the rover to drive as far as it could with the power it had for each sol. A sol is a Martian day. It's 24 hours and 40 minutes. But at best, you normally get about 4 hours of driving in Martian summertime. And just drive as far as you can, do it all again the next day, because it's this nice, smooth, flat, nice, easy stuff to drive over. So when Opportunity gets stuck, they had told Opportunity to drive about 250 meters that day, expecting to get about 170. And Opportunity was good, drove 20 meters, got stuck in the sand dune, and then spun its wheels for another couple hundred meters worth of driving. And the rover's thinking it's driving along as it spins its wheels and digs into this sand dune. The solution turned out to be just put the rover in reverse and go full throttle to get back out. But that took, these images you're seeing go over several days. You can see the shadows kind of jump around a little bit on it. And that's as the rover just spins its wheels, and then finally gets traction and pulls itself out. That led to a lot of new rules of how we drive the rover. We implemented a way of checking to see if the rover is slipping at all. And if it slips too much, stop the drive. And we had to check to make sure we weren't slipping too much every 20 meters of driving. So worst case is you've only done 20 meters of spinning your wheels in a sand dune instead of 200. Of course, some sand traps we weren't able to escape from. So the Spirit rover had a broken motor on its right front wheel. So you'll notice the right front one here is not spinning. This is a camera that's located down on the rover's body that allows us to see hazards in front of it. And the robotic arm has been moved up out of the way so that we can take these images. You see the shadow of the robotic arm kind of doing the shadow puppet thing here on the left side. And we got stuck and just broke through. We couldn't see this. This wasn't a sand dune. It looked like it was going to be actually good driving, but dragging this anchor, the wheels spun and broke through. It's like walking on snow that's melted and refrozen a little bit. And when you step on it, it breaks beneath your feet and your foot drops all the way through to the bottom. Same thing, but it was what is now thought to be a old hot springs vent. So imagine Yellowstone hot springs or any other hot springs, but dried up for several million years. There's going to be this nice fine powder, talcum powder fine that you'll be stuck in. And we tried to get out. This is from our last ditch effort to try and get the rover to a safe place to survive the Martian winter by tilting its solar panels towards the sun. So instead of driving out the way we came, which is what we initially tried, this is driving, trying to get to the edge of this hot springs vent and then park just on the very edge of it to try and survive the winter. So this is actually the last set of driving that the Spirit rover ever did in this movie. And the rover, of course, is still there to this day. We lost contact in March 2010. Dust storms. This is fairly timely as we had a global dust storm, the most severe that we've ever observed at the planet Mars this past summer. So the 2018 storm was much worse than the 2007 storm. And in the book, Mark Watney's driving along and kind of notices, oh, my power levels aren't recharging as fast every day. And dust on Mars in the sky can actually really have a major impact. Even if it's something where you still think it's a fairly sunny day, you lose 5% of the sunlight and you have 5% less charging on your solar panels. So your batteries don't charge up and then you can't drive as far the next day. And if your life depends on it to get to the rocket to take you home, you really need to be able to drive as far as you can every single sol. And we have satellite imagery of this. So this is a regional dust storm on Mars in the southern hemisphere down here. So the couple call-outs, this is not the same maps that Fred put together. We've got Schiaparelli Crater, where the end of Mark Watney's drive is supposed to be, and the Ossidalia Planitia area where he starts. And of course the Opportunity rover down here, Curiosity rover over there for the current group at Mars. And these regional storms crop up. There's actually one went through Mars, the southern hemisphere a few weeks ago. And what we found interesting is setting this whole book in starting off in Ossidalia Planitia. The thing we worry about for storms with the Opportunity rover was these dust storms that would kick up and follow what is called the Ossidalia storm track, because the storms start up at Ossidalia, where Mark Watney was stranded, and then work their way down to Opportunity. So regional storms are big. I mean, that's covering a good chunk of the southern hemisphere of Mars. And regional storms will last for a week or so. They're not terribly bad. They do block a ton of sunlight, but they're survivable. You just do a lot less science while they're there. So this is the 2007 storm in an animated sense, with a few call-outs of Martian locations. The circle that's not labeled is the Opportunity site at Meridiani Planum. And early in the storm, you can still see the surface of Mars pretty well. And then by the end in July of 2007, it's just a big fuzzy planet. And some of our earliest looks at Mars with the Mariner spacecraft showed the same thing. A few of the flybys were during dust storms, and all you could see were the tops of the major dormant volcanoes on Mars. So being able to know that this happens, the camera that takes this is also on the Mars Reconnaissance Orbiter. It's called MARCI, the Mars Color Imager, and we get weather reports. If you're working on a rover, you will get a weather report saying there is a local storm building up near you. It is this many hundreds of kilometers away. It is moving at this speed, and from that, we can tell, okay, that storm will be on top of us in 2 sols, 3 sols. Okay, it's 10 sols out. We may not have to worry about it. It may go away before it gets to us. This is the 2007 storm. So at the time, this was the worst dust storm that a solar-powered rover had ever survived. It was the only global dust storm that Spirit and Opportunity both saw. So on the left, we've got 39% direct sunlight. That was pretty typical for that time of year. The number up at the very top is tau. It's a measure of the opacity of the atmosphere the scientists use. And we get good at translating that into kind of a mental gut feeling of how much power we're going to lose due to dust in the sky. So as the storm progressed, it went very, very quickly. The sol numbers are down at the bottom. In 15 sols, because the first image we just kind of took as regular science imagery, we saw the sunlight decrease from 39% of the sunlight that was reaching Mars was making it to the surface just through the regular atmosphere. That was down to 5.5%. Dropped to 1.7% 5 sols later. Increased to 2.2% 8 sols after that. And we thought the storm was ending. And we're like, this isn't bad. We were able to get through this. So we started planning all sorts of activities with the rovers. Yeah, then Mars decided to make the storm worse. And 2 sols later, it went down to less than 1% of the sunlight reaching the top of the atmosphere at Mars was making it through all of the dust into the rover's solar panels. And then from that, the solar panels are only converting about 30% of that into actual usable energy. So we had to do an interesting trick. The rover has emergency heaters. So if it gets too cold, it turns on these heaters. With the dust storm, the high temperatures were decreased on Mars. So it was colder during the day. It was thankfully a little bit warmer at night. And with low power, our first gut feel was, we can't do anything. Shut down all the science instruments. No, don't talk to Earth every day. Just whatever we need to do to save energy. The rover started getting cold. And so cold that there was a chance those heaters were going to turn on. And those heaters are like a space heater in your house. They draw a lot of power. And if it did, it could deplete the rover's battery. So we did a very counterintuitive thing. We told the rover to turn itself on and just stay awake for an extra 30 minutes every day. And that was enough because just like your laptop will warm up or your cell phone warms up if you're using it a lot, the rover generates extra waste heat from its electronics running. And that allowed the rover to survive. It was still, I remember when it was suggested of, we need to use more energy to save energy. And until the engineering team got the full explanation across, everybody was kind of looking at our chief engineer with kind of, it was polite, but you could read it in people's eyes of, you're crazy. This isn't going to work. It was exactly what saved Opportunity during that global dust storm. Spirit didn't have it nearly as bad on its side of the planet. It only got to about that down to 5%, and we could skate through that for a week or so. Let's see. Yeah, this is the start of the latest storm on Mars. So this is the summer 2018 dust storm. The blue dot's Opportunity. So that would put Schiaparelli Crater down over here, Oscidalia Planitia up here. These are big billowing dust clouds. That's how much dust is in the atmosphere of Mars. They look like just big puffy clouds, but it's just dust that's been kicked up over the years because the dust is ground into these very fine particles from flying around the surface with the wind being able to lift it up. In fact, these dust storms get so strong, it will lift sand-sized particles up. So it's almost a sandstorm at the surface level. Texas A&M University has Dr. Mark Lemon, who is one of the premier Mars atmospheric scientists. He's the one that tracks the dust in the atmosphere for us. If he tells you there's this much dust in the sky above your rover, his number is the number you trust. So this is a simulation that he put together of the 2018 storm. On the left is what a typical day would look at if you were aiming at the sun. It washes out the camera. It's a big bright ball. And then it gets darker and darker. About in the middle here is about as bad as the 2007 storm got. So the maximum tau, as we call it, the one that got us down to 0.9% of the sunlight getting through, was at a value of 4.7. The maximum tau estimate for the 2018 storm is 11.2. That's down to well less than half of 1% of the sunlight getting through. And even the sunlight that's scattering off like a cloudy day, just like it is outside here, you kind of have this brighter sky, even though you may not be able to see the sun all the time. At that point, it's even dark with the little bit of scattering you'd see. So dust storms on Mars are no joke. Thankfully, in the book, it was just a local storm, so Mark Watney was able to find a way around it and soldier on. But getting caught in a global storm midway between two habitats that you can survive in would have been deadly. This is why I doubt we'll send humans to Mars if we're expecting a global dust storm. So, after many lunchtime conversations, one appearance by Andy Weir at JPL to talk about the book and his motivations for writing it, and a few rover drivers squinting at the map, we realized that we probably wouldn't have gone that direct route that was discussed in the book. My vote originally was the blue line. Follow the drive back down to the Pathfinder lander site where you've already driven once. It's always easier to find your way through familiar terrain, even if you've only driven it one time. That's better than zero. And then cut up Ares Vallis, cut across. Being an Opportunity rover driver, this would allow you to stop by and see the Opportunity rover, and then continue on to Schiaparelli Crater, get in the rocket, go home. Another option is to cut across the northern plains and then drop straight down. It's probably a slightly shorter drive. And that's the purple line that we came up with. That was Serena's top choice for being able to get through. So we came up with these options. We actually showed these to Andy Weir, and he was very appreciative that there are people at JPL that are big enough nerds that they spend their lunchtime discussing how to get a fictional astronaut across the surface of Mars. It's what we do at JPL. So with that, I will open it up to questions, but I just want to make one comment about this image first. This is a composite image put together from actual images from the Opportunity rover looking into a valley called Marathon Valley. It's on the west side of Endeavour Crater. A 3D model of the rover made by amateur enthusiasts that track this mission. So they've built their own 3D model, and then some of those other I hate to call them amateurs because their image processing skills vastly outstrip what we use for science. Scientists want to process an image to get scientific data out of it. These, for lack of a better term, citizen image processors, they do it for the beauty of Mars. And that's something that you can sometimes lose when you're looking at the science data, is the beauty and the adventure of the whole thing. So a bunch of them took the images. So the NASA, JPL, Cornell, ASU is the camera from Opportunity, the color panoramic camera. James Sorensen processed it into this beautiful view, added in some extra sky at the top. So this is photoshopped. And then you've got the rover model from some other folks. Christian Lopez put together the rover model, and Sean Duran is a absolute wizard at processing images from spacecraft. In fact, his processing of images from the Juno mission at Jupiter were featured on the cover of Science magazine. He's that good. So I just wanted to give a shout out to all of our faithful followers, fans, and those that are showing us the beauty and the adventure, even though sometimes our heads are looking at nothing but numbers and telemetry. So that's the first half of the talk. So I'm willing to take any questions on how we would get Mark Watney from point A to point B. I've got microphones up. Look at you, Nick.
Hi, my name is Bob. There we go. Hear it? What about the pressure of the wind on Mars? I think the movie The Martian presented pressure as being significant, but I think I read or heard elsewhere that it's very, very light because the density of the atmosphere is very thin.
Yeah, that is correct. The density of the Martian atmosphere is between 0.1% of Earth and 1% of Earth, depending on where you're at. So that whole big dust storm at the beginning that makes the whole movie go is very unrealistic. It was throwing around, in the movie at least, particles about the size of your finger, which is beyond the capability. The wind just doesn't have the force. So if you had a 60-mile-an-hour wind and you were standing there in your spacesuit, you wouldn't even notice it was happening. You might see a few dust particles floating by, but you wouldn't process it at all.
This is Irene. So you have these satellites sweeping around Mars, taking constant pictures and sending them back. And is this would be like a GPS system for, is this how this is going to work? Is it all getting better and better organized? And how many of these pictures are being, how many satellites are taking pictures?
So it's not a GPS system yet. There has been discussion of, in the future, deploying a very bare bones GPS type system. So at Mars right now, we have several satellites. We have 3 from the United States that are functioning: the Mars Odyssey orbiter, which launched in 2001, Mars Reconnaissance Orbiter in 2005, and the MAVEN orbiter, which is looking at the atmosphere, that launched in 2013. There's also a European mission there called Mars Express that's still functioning. It arrived at Christmas 2003. And there is an Indian spacecraft orbiting Mars in a much larger orbit, so it takes nice, beautiful pictures of the whole planet. And there is another European orbiter called the Trace Gas Orbiter that has also recently arrived at Mars, which carried along a demo for a lander with it. And so those all act as communication relays, with the exception of the Indian spacecraft. So a U.S. lander can talk to the European satellite. A European lander in the future could talk to a U.S. satellite, and we work all of that ahead of time so that we can make sure that we have communication. So while it's not yet GPS, we do have kind of an interoperable system there that's laying the groundwork for a future GPS-like system at Mars.
Well, as you said, we're not going to send anybody up there until we can accurately predict the dust storms. How accurately can they predict the dust storms?
It's actually getting better. New research has started yielding. So this 2018 storm, there was a new computer model that was working on predicting it. The old rule of thumb was every 3 Mars years we would have a global dust storm. Unfortunately, we had evidence of it happening every 2 years or every 4 years. So it's just an average. It didn't work out very well. So the new model is still not perfect. It said that we were going to have a global dust storm either in 2016 or 2018. It said there was a 60% chance of 2016. But if the storm did not occur in 2016, there was an 85% chance of it then happening in 2018. So we're getting better, but you can find times in between, because if a human's not going to be there for a full Mars year, which is about 2 Earth years, we can find a little window of opportunity to send a crew to the surface, have them do their thing, and get back before the storms get bad.
This is Charlene. In looking at the maps, what's the process for naming all those sites? I didn't know how to pronounce some of those.
So there's a process has now been developed. Originally, it was just whatever big things and the science teams wanted to call them what they did. So the International Astronomical Union, most people know them as the folks that said Pluto is no longer a planet. They have naming conventions for all sorts of different planets and moons. On Mars, it varies. So Opportunity, for example, visits craters, and our unofficial nicknames for a lot of these craters, and most of them are so small the International Astronomical Union didn't care what we called them, is ships of exploration. So we had Eagle Crater after the Apollo 11 lunar lander. We had Endurance Crater. We had Endeavour Crater, which is big enough that the International Astronomical Union cares. So we wanted to name it after the ship, the HMS Endeavour. And the naming convention for craters of that size on Mars is towns with less than 100,000 people. We found Endeavour, Saskatchewan. So we gamed the system so that we could call it Endeavour Crater. So officially it's named after the Canadian town, but it's actually named after the ship.
I'm Karen, and I'm looking at this picture here, and I'm thinking of the Grand Canyon. Do you have some of the craters like Grand Canyon?
There is a Grand Canyon of Mars, Valles Marineris, which, if you had it here on Earth, would stretch from Los Angeles to New York. Yeah, it's big, it's deep, it's an impressive canyon. It was found by the Mariner spacecraft, was the first to take pictures of it, so that's how it got its name. But you do see some of the stratigraphy, and actually the Grand Canyon is used for training a lot of the geologists that work on these missions. I was actually participating in my rover driver capacity at a planetary science field school where the Grand Canyon was the first stop, so we could understand the sandstones and everything we were seeing on Mars. And I'd been to the Grand Canyon before, but not with a bunch of geologists, and I'd seen all of this, and then they're showing me things that I had seen with my eyes but had never actually understood were there. So the Grand Canyon on Mars, Valles Marineris, is probably very similar in some areas to the Grand Canyon here in the United States.
I'm Arthur. This presentation is somewhat like deja vu for me because, as science editor of the Houston Chronicle, I was there for all the Mariner missions. Uh, how long did you work on this movie? And uh, do you think that the radiation problem, if there is one, for humans on Mars is going to be one of our uh, things that we'll have to really address? And I guess the other thing is Insight is about to launch the seismic experiment also, which you might want to discuss.
All right, so just going to go through it real quick. I worked on the mission, so Spirit and Opportunity I worked on for 12 years, and then Curiosity for 6 months. Radiation on Mars, thankfully the Curiosity rover actually has an instrument to measure it, and it's less of an issue on the surface of Mars. It's still much higher than here on Earth because Mars does not have a planet-wide magnetic field like Earth does, so that's complicating. But the nice part is once you land on Mars, half of the galactic sky is blocked by the planet. So you have a radiation shield for half of it. It's the radiation on the way to Mars that's probably going to be the big driver. Astronauts are limited to about a 2% increase in their lifetime cancer risk, and that determines how long of a mission they can fly. And it gets a little tricky at times to see what that 2% actually is. It's a little fuzzy math. And on your last thing, the InSight lander has deployed its seismometer. The wind cover was placed on the surface yesterday. So hopefully they will start making accurate seismic measurements from the surface of Mars here in the next week or so. We tried to do it with Opportunity, but we have those wheels and suspension and everything. And we found that even if I dropped a rock about 3 feet long right next to the test rover here on Earth and tried to measure the vibration from it, it was like it never happened.
Hi, this is Vicky. Can you describe what it's like to drive the rover? What you see, what the room is like, what instruments you use?
All right, so the room is nothing fancy. It looks like a conference room. You walk in the door, it's in one corner of the room. You look in, there's a conference table in the middle and a bunch of computers around the walls of the room. The rover drivers are at the 2 computers. If you walk in just immediately to the left of the door, there's 2 workstations there. The one right next to the door is for what we call Rover Planner 1. And then right next to them is Rover Planner 2. It's called Rover Planner because they thought we would get too cocky calling ourselves rover drivers. So we do not use a joystick to drive the rovers. Everything is computer code. So drive 10 meters forward, turn 45 degrees to the right, drive 3 meters forward. Or we can say, here's a point that we want you to drive to, and the rover has some limited onboard capability to navigate. So it's a lot of just writing very simple commands, and most of the challenge is looking at the images from the previous day at the end of that drive and figuring out how big is that rock right in front of us? Can I drive over that, or am I going to rip the robotic arm off by high centering the rover? At the rest of the planning room, we have other positions. Next to the Rover Planner 2 is the flight director console, making sure the rover is safe and healthy. And they're looking at things like temperatures and battery voltages and motor currents. Continuing around the room, now on the other side, you have the tactical activity planner. They're the person that kind of collects all of the bits and pieces, all the different commands from all the different roles, scientists, rover drivers, and they move them into one big sequence so we can send that to the rover so the rover can do its thing. We send a full day's worth of commands. Sometimes we send 3 days worth of commands because they found that the humans that operate it like to take the weekend off. At the center conference room table, normally facing so they can see the door of the room, we have the tactical uplink lead. They're the person who runs the day-to-day planning, so each day has a new tactical uplink lead. And they make the ultimate decisions on some of the activities. I did that job for a while, and when Spirit first got stuck, we were still trying to drive out of that pit, and the rover drivers said, we keep driving. Our head scientist, our principal investigator, Steve Squires, and our project manager both look at me and say, we want to stop driving and go try out some techniques in the test bed. I heard arguments from both sides. It took about 4 hours to settle that debate. And then my team chief looks at me and goes, you're the TUL, the tactical uplink lead, it's your call. I decided to continue trying to drive back out. Unfortunately, the left middle wheel got stuck on a rock that was buried beneath the surface, and we only moved about 1 centimeter, so that was an embarrassing day as a tull, but it works. Next to the tull is the mission manager. They provide the strategic perspective. So they have in mind, what are our goals for the next 2 weeks, the next month, those sort of things, and make sure we're actually working towards those, especially with a science team that can get very distracted by whatever interesting rock happens to be right next to the rover. We'd backtracked a full kilometer one time to look at a meteorite when we could have driven 100 meters forward and found another meteorite. So the mission manager can override the tactical uplink lead for safety, mainly, so they can just say, I'm not going to agree to send any of these commands to Mars. But that very rarely happens because they're working in concert to make sure we're doing everything we need to do. But at the end of the day, it looks just like a conference room. If you didn't notice that there was all this activity, you'd walk in and go, oh, there's just a lot of extra computers in this room.
Hi, this is Ken. What is the emotion going on? I assume you make the program, you punch the button, it takes an hour and a half to get there. So what are you thinking? What are you feeling when all that's happening?
It depends on what we're doing. If it's a fairly benign thing, like we're only driving 10 meters, it's still, there's the thrill of, I'm driving something on Mars. I mean, when the data comes down, the images come down, you see what you did, and you just moved a robot on another planet. So there's some exhilaration in that. But it's when there's extra challenges. Are you in really challenging terrain? Is the rover having a problem? That one is everything from terror of, please don't let me screw up, because if I do, I've killed a $500 million Mars rover. I've had days like that. And there's other days where you drive into work, there's a sign on the side of the 210 in Pasadena that says, NASA JPL. We have a bigger sign than the Rose Bowl has. And you kind of get this perspective of, wait, I'm going there to drive a Mars rover. They haven't kicked me out yet, so I obviously am supposed to be here. And they pay me to do this for some reason. So you kind of get that 10,000 foot view occasionally. One of my last drives before I left JPL was, we were coming down a hillside on the rim of Endeavour Crater. It was between this big kind of, we called the hills that are the remnants of the crater rim, named them after capes that the HMS Endeavour explored. So this was Cape Tribulation. We're heading down towards a little valley on the south side of that. And one of the things as a rover driver that's a really special thing is if you happen to be able to command a drive that goes more than 100 meters. The Curiosity rover will never do it again because its wheels are getting beat up by the rocks and they just can't see the rocks that far out. And where we had been doing a lot of the science, we had not been able to go that far. Maybe maximum drive distance was 20 meters. And we came in, we looked at the distance that we could see, and we realized we could do a long drive. And I was Rover Planner 1. Rover Planner 2 that day was Paolo Belluta, the most seasoned rover driver there is. He's personally commanded 18 kilometers of driving on the surface of Mars. And at this point, we knew I was leaving the project. And we put it together, and at the end of the drive, we get the data back. We'd gone 131.2 meters. The record is 219.2 meters, and that's back before they got stuck in the sand dunes, so they were allowed to be a little more fast and loose with the driving. And Paolo looks at me and goes, I'm glad you got this. It would have been a real shame had you not been able to get a 100-meter drive in. Of course, that day I was trying to argue for driving 160 meters, so the 130 meters was the short option, but that was the one of the absolute thrill of, I've done something that, depending on what happens with the Opportunity rover and with Curiosity, may not be surpassed until the Mars 2020 rover gets there. So that was a kind of career high point for me.
We are incredibly lucky that we got to salvage this project here.
Yeah.
We're having a great time. We'll take a 10-minute break now. And
all right, so unlike the last half of this talk, which I've been evolving over many years, this is a new one. So I recently started in a PhD program at the Colorado School of Mines in space resources. It's a fairly interesting field, and working full-time as a systems engineer, it's partially because I am very interested in the topic. It's a very multidisciplinary field right now. It involves geologists, engineers, economists. It is a kind of brand new thing, which is nice because you're not doing research on the minutia of what some individual scientist needs to support their research grant. So there's a lot of free-for-all on being able to study what you are very interested in, because there's just a ton of room to advance how we do things in space. So I also joke it's because I have an allergic reaction to having free time. So I signed up for extra classes. So with my hat on as a PhD student, this is going to be hopefully a pretty good talk about space resources, and the main reason is we want to live off the land in space. So the International Space Station is kind of our foothold off-world. It's been permanently crewed since late 2000. So I grew up as a child of the space shuttle era. I was born after the first space shuttle launch, so that was my baseline for normal. Now you have kids, their baseline for normal is we have always had astronauts in space, and we've always had rovers on Mars, so things are moving forward. But the space station's using space resources right at this moment, even though we may not have called them that when we started building it. We have all those solar panels. Solar power is a space resource. It's coming from the sun. It's not coming here from Earth. If we just had to keep launching batteries up to the space station, it wouldn't last very long. So 120 kilowatts is enough to power about 40 American homes. So the solar panels do quite a bit of work on the station. The little ones that are called out there are the Russian module solar panels, and those are what powered the space station in its early days before we got the nice big solar array wings that were launched by crews on the space shuttle. So space resources are more than just solar power. That's the big one that most people use. You got volatiles. So this is things like helium that's found buried in lunar dust, the solar wind deposit, it's there. You've got hydrogen, you've got all of these other materials that are these lightweight chemicals that if you take them out of however they're trapped in a rock can dissipate very quickly. But those tend to make good rocket fuels or other gases you can use. You've got minerals. Like we do here on Earth, you can convert a lot of the rocks into usable minerals. I ended up doing way too much reading on getting sulfur out of lunar rocks to make concrete. Of course, metals, you've got asteroids. The metal asteroids are just pure metal. There was the whole group that wanted to go mine a platinum asteroid because they can make all this money, even though they would probably make platinum about as valuable as aluminum foil. You've got ices, which is nice because if it's water ice, you can use that for all sorts of things, mainly water to drink. Trash, believe it or not, is a space resource. That's things that the crew will throw out, or any bodily waste falls in that category. Gases, so atmosphere of Mars, can be used for various things if combined with other chemicals. And derelict spacecraft. Just because a spacecraft's radio has failed doesn't mean its solar panels don't work anymore. So going and repurposing dead satellites is also a potential space resource. Speaking of ices, this is a picture from the Mars Phoenix lander. When it dug its first scoop on Mars, it found ice just below the surface. It landed up at the high latitudes just shy of the Martian polar ice cap. So we have found water on Mars. It seems like every mission that goes to Mars finds either evidence of past water on Mars or evidence of current water ice on Mars. So I'm just waiting for the next mission to once again find water on Mars. So inside the International Space Station, they're continuing with their space resources. As the station's been built out, it has gained new capabilities. They're able to recycle water. Primarily, it's from the bathroom. And they joke that it's turning yesterday's coffee into today's coffee. They also pull the water out of the atmosphere because every time you exhale, you're breathing out water along with carbon dioxide and a bunch of other stuff. And they can pull that out of the atmosphere and repurpose it. And to be able to send humans to Mars, where we can't send up new tanks of water, that's going to be very important. Of course, there's air recycling. There's splitting the carbon dioxide off so that then we have oxygen. It's important. And plastic recycling is the new thing to reach the space station. A company had sent up, called Maiden Space, had sent up a 3D printer several years ago, and they sent a new device called a refabricator, because Star Trek has trademarked replicator, to the space station that can grind up those plastic things that they print with the 3D printer and turn it back into the material that feeds into the 3D printer. So if you needed a wrench, you could print this special purpose wrench, do the thing you need, shove it back in the refabricator, it grinds it up, turns it back into the raw feedstock for the 3D printer, and then you can print the next wrench. This way, they're trying to make it where they can recycle the packaging. So if you send up supplies to the space station, the packaging can then be processed in, and you can make new tools, new bulkheads. It's a very important piece of technology for future missions, and it's nice that we're testing that out. And since I did just take a picture of the inside of the space station, the crescent moon, that is the space station bathroom. It's right next to the gym. That's the treadmill. You run on the wall. So the next step is going to the moon. And this is political winds have been shifting between the moon, Mars, asteroids. Ignoring all of that, there's a commercial push to go to the moon. So it's probably going to happen just independent of where major space agencies are aiming at any given administration. So there's water trapped on the moon. This is a picture taken by the Japanese lunar orbiter. They sent an HD camera up, and it's actually out of one of their videos. So there are permanently shadowed craters at the bottom of which never see sunlight on the moon between 78 and 90 degrees latitude, both north and south. And they found that water ice is trapped in with the dirt on the surface. There could be a lot of water ice, plenty there. And some of these are, it's a little hard to see on the screen washed out, but they're permanently shadowed craters in here. You can see those nice long shadows being near the pole. The nice part is there's also peaks of eternal sunlight, as they call them, where if you're on the edge of these craters, the way the moon rotates is you can always see the sun. So that's helpful if you want to go there and do things near those permanently shadowed craters. So water can fuel rockets. Some of the most efficient rocket engines we have are powered by hydrogen and oxygen, so I promise not to get too much back into high school chemistry. But if you take some water with electricity, you can make hydrogen and oxygen, and that can fuel things like a lunar lander. This is Lockheed Martin's concept for one big lunar lander that would fly all the way down to the lunar surface from a space station in lunar orbit and then go back up. There's new ideas of how to do lunar landers from that space station that NASA's playing with, but all of them are looking at having the capability to be refueled at the moon in advance of even if we have the ability to make fuel at the moon. So they're thinking ahead of how can we build a sustainable way of going to the surface of the moon, because if that lunar lander there would probably cost, I'm going to guess, $500 million, $1 billion or something. So if you throw it away every time, you're not going to be able to keep going to the moon. If you can use it like we did the space shuttles for 20, 30, 40 missions, now you've got a return on your investment. There's no such thing as a free launch. The United Launch Alliance in Denver, Colorado, they are a conglomerate between Boeing and Lockheed. They build and operate the Atlas V and Delta IV rockets. They did a study looking at what would it cost if we made fuel on the moon. And then we had to get it back somewhere to be usable, because you're not going to land everything on the moon just to refuel it. So the cost of liquid hydrogen, liquid oxygen fuel on Earth is not terrible. It's about $4 a kilogram, and that's for the absolute rocket grade, high octane, everything you could possibly want. So if we launch a kilogram of that fuel from Earth, it's $4,000 just to get it to low Earth orbit. We want to send that out to geostationary orbit, where most of the communication satellites are, $16,000 for each kilogram of fuel that you want to carry with you. If you want to get to the Earth-Moon L1 point, which is a balance point between the moon's gravity and the Earth's gravity, it allows you to just kind of hang out in space, suspended between the Earth and the moon, $12,000 a kilogram. And if you want to take that fuel with you all the way to the surface of the moon, $36,000 per kilogram. That's getting pretty pricey just so you can have gas to get home. But if you can make the fuel on the moon, they figure making it on the surface of the moon, once you've deployed all the equipment to do so, you can get it down to $500 a kilogram to have that fuel sitting on the surface of the moon. You put that in a rocket on the moon, since lunar gravity is much less than Earth, you can get that up to the balance point between the Earth and the moon for $1,000 a kilogram. You can get it to geostationary orbit, so now you're getting close to Earth, into the Earth gravity well, $1,500 a kilogram. If you want to get down to low Earth orbit, where the International Space Station is, which is really far into Earth's gravity well, $3,000 a kilogram. Of course, there's an upfront cost to doing all of this on the moon, so that's not fully rolled into these values. But there's a chance that if we start taking lunar water and turning it into this rocket fuel, we can actually reduce the cost of exploring even just the moon by refueling in low Earth orbit, or missions to Mars or asteroids or outer planets, because the fuel cost has become cheaper and it's in a reusable system. So the image here shows the Orion space capsule that is being developed by NASA and the European Space Agency, docking to one of those space stations in lunar orbit, which is likely going to become a gas station as well. One of the big problems, though, that we're finding with space resources is storing fuel from water isn't easy. So you've got this nice big chunk of water that you've split off. So you start off with 1 cubic meter of water. That's about 1,000 kilograms. Well, you make it into its liquid oxygen, liquid hydrogen components, and you end up with these two much bigger tanks, and I've scaled these cylinders. Liquid hydrogen is still not very dense. It takes 2.8 cubic meters for what you got from that water. The liquid oxygen is just under a cubic meter, so now you need these big fuel tanks. Another big problem is you have to keep it cold or it tends to want to expand. You've got liquid oxygen down at minus 182 degrees C. It's pretty cold, but for rockets, if you've ever seen the videos of anything from the Apollo launches, all of the rocket stages had liquid oxygen in it. Or a modern Atlas V or a SpaceX Falcon 9, they have liquid oxygen in them as well. That's kind of the white ice that you see on the outside falling out. That's because they don't bother insulating the fuel tanks, because they can keep the liquid oxygen cold enough for long enough to launch. Liquid hydrogen, on the other hand, is why the space shuttle's fuel tank was bright orange and covered in foam, is to help keep ice from forming on the outside, but also keep the fuel cold until it's time for launch. So it's got extra complicated factors. Also, liquid hydrogen is the teeny tiniest little atom we've got, and the H2 molecule is also equally tiny. And it can leak out, so you require special welding and being very careful about your material selection, or else you're going to have all of your fuel leak out of your holding tank. So you can make this on the moon, but it may just disappear and evaporate out of your tank effectively. So the picture here, to give you an idea of scale, is the inside of a fuel tank for the new Space Launch System. It's the same diameter as the Space Shuttle's fuel tank. This is one of the test articles that they're welding together. So and this is inside the liquid hydrogen tank, to give you an idea of how big of a tank we're talking. So this lets us get to a space gas station idea of, okay, we've been able to make this fuel, we're able to launch this fuel, we need to store it somewhere, but we need to keep it really cold. So the best idea we have is put the fuel tanks behind a sunshade, because sunlight hitting your fuel tank will heat it up, and then your liquid hydrogen starts boiling, and if you can't vent that pressure, which means dumping fuel overboard, your tank will explode, which is a bad day for everybody. So there's an idea to put these sunshades up, but then you need a place to dock to refuel things, and now you need your own spacecraft or rocket stage to keep this flying gas station pointed in the right direction, because the problem is you point that sunshade at the sun and suddenly you're collecting all of this sunlight right next to your fuel tank, and it will then heat up and possibly explode again. So this is an idea that has been looked at of how to keep the temperatures where they're at. There's other ideas of using that extra little bit of hydrogen and oxygen that'll boil off and vent and be gases to run through a internal combustion engine that, instead of running on gasoline and air, is running on oxygen and hydrogen. They've actually started doing research with the Formula One race car engine provider, because they're used to high temperature engines that can handle that fuel combination. And that would keep the pressure up in the tanks to help keep everything liquid. But that's good for 6 months at most right now, and that's just on the ground and making sure we've got everything right. They haven't tested that in space. So that's one area that space resources are looking into, especially for those of us on the engineering side, is how do we solve some of these problems? It may not be the actual resource, but it's making sure that we can transport and control and have all of these resources going. A lot of engineering goes into gas stations, both here on the ground and in space. The big thing that kind of excited me about all of this is I'm, as you can tell from earlier, a very Mars-centric person. So there's been a push to go for Mars using a mission just straight to Mars orbit to start with. Lockheed Martin's been an advocate of this. The Planetary Society's been an advocate of this. And they're starting to realize that we can use this fuel that we could potentially mine from the lunar South Pole and use it to fly to Mars, use it to fly back from Mars, use it, heck, to land on Mars potentially. And Lockheed came up with this idea. It's a very beautiful render, and they've actually shown how you could put it on rockets and pieces to create this Mars base camp that would be, everything in here would be fueled by liquid oxygen, liquid hydrogen for its main engines, including these little excursion vehicles docked on the end. That's based off a rocket stage that already runs on liquid hydrogen, liquid oxygen. The gold tanks are storing extra fuel. So it's a flying depot. One of the biggest problems we encountered was, of course, people saying, okay, you're going to send this stuff to Mars. It's going to take 9 months to get there. How are you keeping your liquid hydrogen from leaking? How are you keeping it cold? Do you have a big enough tank to carry all the stuff you need? And reading the papers, I'm pretty sure it was in the Lockheed Martin update on their Mars base camp concept, it dawned on somebody, if you don't need it as fuel during your trip, why are you carrying it as hydrogen and oxygen when water can be kept liquid at very reasonable temperatures for very long durations? And why don't you just send a big tank of water, and then you have these huge solar panels, so you just add that electricity again, it splits the hydrogen and the oxygen, and you can make your fuel from water either brought from the moon, you can launch it from Earth if you wanted to, and you can make your fuel at Mars for your space station. Or you can make it at the moon for your space station or near an asteroid and transport this incredibly efficient fuel where all you need to turn it into fuel is just a solar panel as your power system. It was an kind of an intuitive breakthrough that is so elegant in simplicity that a bunch of us that were following this concept were kind of wondering why we hadn't thought of it first. So they've looked at that, and you could just send tankers out. And that's why a group is starting to look at how do you build everything you need for even just going to the moon to be able to use that similar concept. Lockheed, that lander that I showed several slides ago, they were talking about, let's make it refuelable. Let's do the refueling in lunar orbit. Even if we have to launch water from Earth to prove that it works, if we can't get the water from the moon quite yet, why don't we build it so in the future similar designs will evolve off of this, just how rockets and spacecraft all evolve as they become newer and more advanced. Let's just have this as a thing we do, because it's, to kind of use the analogy Elon Musk had for having reusable rockets here on Earth. You don't fly a 747 to London and then throw away the 747. You want to keep using the same thing. So yeah, that simpler tanker would be able to enable solar system exploration. And because you don't need to make the fuel fast. If you don't have a human there that needs the fuel right this second, okay, it takes you 6 months to convert all of that water to the fuel you need. But we have demonstrated storage systems that can store fuel for 6 months. Okay, if I don't need to go home right now, I need to go home in 6 months, yeah, let's take 6 months to make the fuel. That's an area of research that is starting to move forward very quickly. This is another shot of the Mars Base Camp concept with one of the excursion vehicles coming back in, but in their concept, that could be a tanker coming in from Earth or the moon, ready to help things out. It's been taken a step further. So space resources, the first time I think I was ever exposed to the concept was a talk in the late 1990s by an engineer that was at the time working for Lockheed. It was actually he was working for Martin Marietta. It's before all the big aerospace mergers started happening. Named Bob Zubrin. He wrote a book called The Case for Mars. This was even before the book came out. And he gave a talk to a local Boy Scout group. I was one of the Boy Scouts. And it was about how we're going to go to Mars. And he showed us pictures of Wernher von Braun's ideas of how we're going to send humans to Mars in the 1980s. Granted, this talk was in the early 1990s, so that didn't happen. And he was a proponent of a concept called Mars Direct. And with that, you would have one launch. It would go straight from Cape Canaveral, Florida, to the surface of Mars. little ambitious, but a core technology he had in that was a reactor that could take hydrogen brought from Earth, because that's before the Phoenix lander was there and showed that you could potentially find water ice on Mars. And you can combine that with the carbon dioxide that makes up most of Mars's atmosphere. Here on Earth, it's mostly nitrogen. Mars is mostly carbon dioxide. You can combine that, and through this Sabatier reactor, it will then spit out methane, which is also a very good rocket fuel, and oxygen. So you could use that to fuel your trip home, and then you'd go straight from the surface of Mars back to the Pacific Ocean. So that was kind of my first way back exposure. Well, Lockheed has the same idea, but since they have experience with a hydrogen and oxygen rocket fuel engine, they've come up with this big Mars lander design, and because of the fuel you need to be able to land and then get back up if you don't want to leave half of your rocket on the surface, they end up being these huge rockets. Their lunar lander concept I showed you is basically this without the fancy aerodynamics. It would refuel potentially using water brought from the moon at the surface of Mars. So it's a real major enabling technology. The area I'm going to very likely do my thesis research on is how do we get water at the surface of Mars so you don't have to lug it all the way down? Can we start doing Mars water, mainly to start off with for astronauts to drink, because it's a lot less than trying to refuel something. But my focus is going to be down at the equator of Mars. There's no water ice. There's no glaciers like there are under the surface at the mid-latitudes at about 50 degrees north and south on Mars. But there's enough water bound up in the local sandstones and the clays and everything that you can bake out. And you might be able to produce enough water to make, in the farther future, after lunar water becomes a common thing for making propellant, Mars could be potentially for small missions with 4, 5, 6 humans on the surface at a time, sustainable using water sourced only from the planet Mars, which would be a game changer because then again, you don't have to fly all of that water from Earth or the moon or anywhere else. Also, then if you end up having to stay on the surface for an extra 2 weeks, month, year in the case of Mark Watney, you can actually keep making water for yourself so you don't have to die, because a big adventure in the book and a big explosion in the movie were based on him trying to make water. That would then lead into, you don't have to use oxygen and hydrogen as the fuel. Now you can very quickly start making methane fuel at Mars and have more compact rockets to head off elsewhere in the solar system. Because in our solar system, Earth is the 3rd planet, Mars is the 4th, and then between Mars and Jupiter, there's the main asteroid belt, which is divided into 2 parts. The inner part, which is the rocky part, it's closer to Mars, and the outer part, which is the icy part, where there's more water and other ices. And farther out in the future, that can be another resource stop. So space resources is getting into a field where it's very forward-looking in the future. And Mars has been 20 years away for my entire life, so it's still very much 20 years away. But the problem is now much better understood, and it's no longer being looked at as a flags and footprints mission. I mean, there's national pride that'll come with whatever countries, and it's going to be more than one supports the first crew mission to the surface of Mars. But every little bit of technology needs to be developed somewhere. And space resources is the whole economic, we can make money in space. That's not my part of space resources. Mine is enabling technology to allow exploration to continue and be sustainable and be permanent, because that's my passion. So it's interesting to take these concepts and work backwards from my Mars rover knowledge to how do we do something that may allow us to have those first missions. So that space resources covers, well, pretty much everything if you're using anything not on the planet. It's a very broad field again, but it's got a lot of potential to revolutionize space flight and kind of move to the next era, because right now we're still very much just government-funded missions, soon to be tourist missions, but that's just dipping our toes in the water of what we can do. And hopefully we'll be repurposing it, and maybe someday someone will be using the derelict spacecraft, much like we saw in The Martian, going up, using those radios to phone home if they have to, or maybe it's just, hey, those batteries are still good. We might want to use those on our rover. because the batteries on the Opportunity rover are projected, if it wakes back up after this global dust storm, to last until about 2040. So the batteries are still pretty good. Hopefully some humans will end up getting some use out of their extra capacity. So this was a much newer presentation, much shorter presentation. So I'm going to open it up to questions. Feel free to circle back to the Martian road trip presentation. So this is going to be a lot more of a free-for-all.
This is Lucy here. Question about the volume of water you're talking about, and if you start using it to make fuel, how long would that last before the water on the moon or on Mars is used up?
So that is a very critical question. One of my project I was working on, I actually was on a team design meeting on, we're trying to come up with a system to get better maps of the lunar water. At a minimum, so like fueling this Mars lander, for example, let's just use that as a baseline. We should be able to take several football field size areas because the water ice may only go down about a foot. And it depends on how much is mixed in. It could be up to 25% of the total volume there is what we would need to convert for one mission. But there are thousands upon thousands of square kilometers of this water ice in the permanently shadowed parts of the moon. And the goal would be kind of, can we use that before we run out of the easy to get stuff? Because then it's just a matter of how much effort we want to put in to get the resources out. Can we then switch to, asteroid water or something else? Mars is a little bit trickier. There's glaciers under the surface, which is nice because it's already ice. We don't have to worry about it. Then those are huge, hundreds of square kilometer glaciers. But you have to drill down. You have to get through the dirt. That's why I'm looking at can we just bake the water out of the old sandstones on the surface? It's easier to get to. But it's not something where even if we suddenly had the system operating tomorrow that I would be worried about running out in my lifetime. If I have kids in their lifetime, we've got hundreds of years of capability there to then come up with the next solution out there to keep going.
This is Ken. My question is related. I'm wondering what kind of an operation is recovering that water. Is it a big surface mining operation, and then heating it up and recovering the steam or something?
That's the question. That's actually one of the other design projects that's going on as well. Is there's an idea of you just literally dump the dirt and ice in trucks, carry it out somewhere, heat it up as steam to get it out. Which another idea is you could put a tent, seal it to the surface somehow. And then you can actually reflect sunlight and just use the heating, because you don't have to heat it up much from the permanently shadowed because the vacuum of the moon, it will immediately start to try and boil off. It can't be trapped in there as well once you heat it up just even a little bit. And then that would just collect in that tent, and you'd then have a cold plate just to have a condensation on, and you collect it from there. So I'd say those are the two main ideas for how to do it. There's probably about another 3 or 4 dozen floating around but until we get down on the ground and we actually see, okay, how much is the ice actually mixed in? How deep is it? It's all educated guesses, but there's research even from Colorado School of Mines to NASA to the Chinese a lot of people are looking at how to do it. It's just, what are we going to actually find when we get there?
This is Bob again. That was my question, but I'm going to word it because I think I'll get a slightly different answer. You can do all your brainstorming you want on Earth, but we really need to know what is there that can be used. I'm not talking about the stuff we take with us, but the material that we find there. And to what extent, this is the way I'm going to phrase the question, to what extent is planetary resources or space resources driving the scientific agenda regarding the analysis? It's one thing to detect water, but that doesn't tell you that it's pure water. It could be mixed with methane, dust, and other things. And you need to know that as an engineer.
Oh, yeah. So the driving future science missions, that we actually had a lunar rover called Lunar Prospector that was recently canceled. The instruments on that to try and help solve some of those questions at the moon are going to fly on commercial lunar landers, hopefully in the next few years. But for the research I'm doing, I think I can answer the question a little more precisely. Since I'm going to focus on the equatorial regions of Mars, where we've sent pretty much our major Mars rovers, and they have instruments that can detect chemical compositions of the surface. The Curiosity rover is a beautiful wet chemistry set on the inside. That is going to feed the information of there's perchlorates, which are a contaminant that would be in the surface material in the equator. And understanding the measurements that have been made by those rovers, the first step I see in the process, and this is what I've pitched to my advisor, is I need to make a copy of the Martian soil, but here on Earth, with all the contaminants. And then we've got a vacuum chamber we can try getting the water out with. And I want to, because one of my big questions is how much of the contaminants go with the water and how much stays in the dirt? Because if we don't know the answer to that, we could just be making our life a whole lot harder. And that could rule out all the research I do could end up being a thesis that ends with, yeah, we don't want to ever do this because there's too many contaminants. So it's hopefully going to feed forward into future missions to get us more information so that we can accelerate the pace.
Paul here. I suppose one idea here is harvest the excess carbon dioxide out of our own atmosphere. But now this is using the kind of the standard fuels we have now, hydrogen, oxygen, and variants on that. What alternative propulsion energy is out there being looked at?
So there was a big moment where there was a group at a kind of advanced physics research group at Johnson Space Center that was looking at electromagnetic propulsion, and they thought they had developed something, and everyone's like, oh, they're going to invent warp drive. Turns out the effect they were seeing was measurement error interacting with the Earth's magnetic field. But you can't figure out the new breakthroughs if you don't try the experiments to start with. So it was good research, even though it yielded a bust. For main propulsion, we've got standard what we call chemical rockets, even though they're all feeding chemicals in as propellant. But we'll just call them chemical rockets, which are the ones where you combine a fuel and an oxidizer and you light it on fire. The main combinations for that are kerosene and oxygen. That's what SpaceX uses. It has a very nice orange flame. Methane and oxygen, which is kind of the new trendy fuel for rockets leaving Earth, at least on the first stage, has a nice blue flame. It's about 50% more efficient than kerosene and oxygen. A little less dense on the fuel, so you need a slightly bigger rocket, but it's slightly more fuel efficient, so you get about the same size rocket. Hydrogen and oxygen is the most efficient chemical combination we have for those chemical engines. It's about 30% more efficient than methane, a little bit under twice as efficient as the kerosene. Has a nice clear flame, so be careful if you're walking around one of those rocket engines. And because the hydrogen's so lack of dense, you end up with a heavier fuel tank, so it's about a wash with the kerosene when first leaving Earth. But once you're up in space, the hydrogen and oxygen is king, except for electric propulsion. And this is where we take a gas, like you can use xenon is the most commonly used for electric propulsion. You can also use argon and a few other things. And that accelerates across a mesh grid that's charged up, and it accelerates just the gas itself out the back. It doesn't give you much force. We've done several missions with it, and imagine just holding a piece of paper on your hand. That's how much force that engine provides. But it's doing that 24 hours a day, 7 days a week, 365 days a year. And if you run it for long enough, you can end up with a larger total velocity change than the chemical engines. So the question is, do you want to get there with high efficiency, or do you want to get there a little bit faster? Those are the main trades. Coming into future missions are going to be solar sails. There was demos. The Japanese had an amazing demo near Venus with their solar sail. They put LCD panels on so they could make the sail black or silver on certain parts, so they could actually maneuver the sail using nothing but sunlight. There's the Planetary Society is working on developing one. There was going to be a mission to the moon until they realized it was easier to use solar panels to do what they needed to do. That was going to actually use a solar sail not only to get to the moon, but to reflect sunlight into those permanently shadowed craters to look for water. So that's kind of the big few that are out there for standard use. But I think for a lot of missions, we'll see a combination of either a chemical fuel. There's kind of a battle for Mars between methane, oxygen, hydrogen, oxygen. Those are the two contenders. And electric propulsion, because, again, if you're sending one of those water tankers out, you could even use water through the electric propulsion. It's not going to be as efficient. But if you got 18 months to wait for the water to show up, you might as well do it the efficient way and not waste anything.
with all the different fuels you're suggesting, CO2 in water seems a little safer than this trendy methane. Do you worry at all about the highly explosive properties of methane, especially if I think I just heard you say it doesn't give quite the thrust that water, CO2, or electrolysis in water?
Yeah, so methane it's more compact. It's easier to store than the hydrogen, so it has as engineers, we do trade studies. So one of the trades is either going to be how big is your fuel tank. Methane's going to be smaller, and smaller normally wins when going to space, or lighter weight wins, which smaller is a proxy for. The nice part about methane's explosiveness is that makes it work really well in the engine itself. So that gives you all of the power coming out. So I think it remains to be seen. And it may just come down to, just like there's diesel cars and gasoline cars, we may end up with both types of rocket engines being used a lot of places, just because one company is offering the methane engine as their option, another company's offering that hydrogen engine as their option. And since both of those are ideas coming from major aerospace companies, I think for the time being we may see that.
Hi, Ken again. Maybe a little out of your area of expertise, but how much frustration is it to NASA that we have our major program changed possibly with every administration and our funding changed possibly with every Congress?
All right, so disclaimer, this will be my personal opinion on the subject. Even though I don't work for JPL anymore, I'm going to be nice and just put that disclaimer out there. There is frustration, but I have seen in the past 6 years, I would say, an incredible group of people, mainly at NASA headquarters, that have started thinking longer term and how you deal with political realities. A group at JPL had a paper on how to go to Mars, where you gave every 4-year administration some sort of big win that they could tout as, here's what we did in space. And it used political optimization as a baseline, which is an unfortunate reality. As engineers, we wish science and engineering would rule, but its money comes from Congress. The technology needed to go to Mars used to be, we don't need to go to the moon. We can just go straight to Mars. Why are we wasting our time with the moon? And the Mars community has started realizing we can test a lot of systems to go to Mars at the moon, in the lunar vicinity. We can contribute to lunar exploration. And as things switch between the moon and Mars, I need to develop a habitat that can keep humans alive without any resupply from Earth for 1,500 days, is about what they're thinking they need for Mars. Well, having better closed loop life support, as we call it, so being able to keep people alive longer with less supplies, works for the moon too. So it's I'm going to work on this lunar mission, and I'm going to work on developing this little piece of the technology, and it will help going to the moon. But then I can use it again over here on Mars. And they've started thinking through longer term of how can our technological roadmap sit with whatever the current political priority is, so that eventually 30 years from now, we have all of the pieces. We just happen to build them in a different order than we were expecting, which has been a wonderful change, because it used to be moon versus Mars and everybody got angry at each other. So I'm liking where I'm seeing the world go with this.
Well, the definition of a good dissertation is one that sparks a whole bunch of other questions, right? Having done one, I know that. But I think you got a good dissertation here. I mean, we exploded with questions for you. So thank you so very much for being here today.